10.8 Energy Considerations in Rotational Motion. The outline of this video is as follows. We will extend our familiar concepts of work, energy, and power to the world of rotational motion, which provides a powerful alternative to using torques and forces directly. First, we will define work and power for rotating objects, establishing the connection between torque, angular displacement, and energy transfer. Next, we will formulate the work kinetic energy theorem for rotation. This theorem provides a direct link between the net work done by torques on an object and the resulting change in its rotational kinetic energy. After that, we will see how to apply the principle of conservation of energy to systems that include rotating parts, combining both translational and rotational kinetic energy into a single framework. To put these ideas into practice, we will conclude by analyzing the motion of a freely swinging rod. By the end, you will be equipped to solve complex dynamics problems involving rotation using these elegant energy methods. We will now derive the expression for work done in rotational motion, which is the foundation for understanding rotational energy. We begin with the fundamental definition of work for a very small displacement. dW equals the dot product of the force vector F and the displacement vector ds. For a point on a rotating object, this displacement is a tiny arc of length r times d theta. Crucially, only the component of the force that is tangented to this arc actually does work. The radial component, which points toward or away from the pivot, is perpendicular to the motion and contributes nothing. This tangential component of the force is given by F times the sine of phi. So the work dW is the tangential force, F sine phi, multiplied by the arc length, rd theta. By rearranging the terms, we get the quantity Rf sine phi, all multiplied by d theta. We recognize the expression in the parenthesis as the definition of torque, which we call tau. Therefore, the work done during a small rotation is simply the torque multiplied by the angular displacement. Now that we understand rotational work, let us find the power delivered to a rotating object, which is the rate at which that work is done. We start with the general definition of instantaneous power, P, as the time derivative of work, W. This is written as P equals dW over dt. From the previous slide, we know that an infinitesimal amount of work, dW, done by a torque, tau, is equal to tau times the infinitesimal angular displacement, d dash theta. By substituting this expression for work into the power equation, we get P equals the time derivative of the quantity tau times d dash theta. Assuming the torque is constant over this small interval, this becomes P equals tau multiplied by the fraction d theta over dt. We can immediately recognize that the term d theta over deet is the definition of instantaneous angular velocity, which we call omega. This gives us our final, simple relationship for rotational power. P equals tau times omega. This is the direct rotational analog to translational power, which is force times velocity. The power delivered to a rotating object is the product of the applied torque and its angular velocity. We can now formally derive the work kinetic energy theorem for rotation, which connects the work done on an object to its change in rotational speed. Our derivation begins with the rotational form of Newton's second law. The net external torque equals the moment of inertia, I, times the angular acceleration, alpha. The key mathematical insight is to use the chain rule to rewrite alpha. Instead of being the time derivative of angular velocity, we express alpha as omega times the derivative of omega with respect to the angular position, theta. After substituting this into our torque equation and rearranging, we get an expression for the infinitesimal work done, dW. Integrating this expression from an initial angular velocity, omega-I, to a final angular velocity, omega-F, gives us the final result. The net work done by the external torques equals the final rotational kinetic energy minus the initial rotational kinetic energy. This means the net work done on a rotating object is precisely equal to the change in its rotational kinetic energy. Beyond the work kinetic energy theorem, we can apply the powerful principle of conservation of energy to analyze systems involving rotation. This approach is especially useful for isolated systems, where no non-conservative forces, such as friction, are doing work. In these specific cases, the total mechanical energy of the system remains constant. The conservation equation states that the change in kinetic energy plus the change in potential energy equals zero. The crucial update for rotating systems is how we define the total kinetic energy. An object that is both moving through space and spinning has energy from both types of motion. Therefore, its total kinetic energy is the sum of two terms: the translational kinetic energy of the center of mass, which is 1/2 mv squared, and the rotational kinetic energy about the center of mass, which is 1/2 I omega squared. For example, a sphere rolling down a hill possesses both translational and rotational kinetic energy. To correctly analyze its motion using conservation of energy, you must include both terms. The essential takeaway is that conservation of energy applies to rotation, provided we expand our definition of kinetic energy to account for both translational and rotational motion. This table highlights the powerful set of analogies between rotational and translational motion. This comparison is a very useful tool because the mathematical form of the equations is nearly identical in both cases. Let us trace the parallels. In kinematics, angular quantities like displacement, speed, and acceleration are the direct counterparts to their linear versions. For dynamics, the central analogy is between Newton's second law. Net force, which causes linear acceleration, corresponds to net torque, which causes angular acceleration, and mass, the measure of inertia, corresponds to the moment of inertia. Therefore, the equation F equals m times a has a direct rotational equivalent. Net torque equals I times alpha. This pattern extends to concepts like work, power, and kinetic energy. For instance, rotational kinetic energy is 1/2 I omega squared, which mirrors the translational form of 1/2 mv squared. Understanding these analogies means you do not have to memorize a completely new set of formulas. You just need to learn the rotational equivalents for the variables you already know. In this example, we will analyze a classic problem. A uniform rod pivoted at one end, swinging down under the influence of gravity. This problem is a great application of the principle of conservation of energy to a rotating system. The rod starts from rest in a horizontal position, and our goal is to find its angular speed when it reaches its lowest vertical positions. A crucial point here is that we cannot use the standard rotational kinematic equations. This is because the torque exerted by gravity on the rod changes as it swings. Since the torque is not constant, the angular acceleration is also not constant. Instead, we will model the rod and the Earth as an isolated system. Because gravity is a conservative force, the total mechanical energy of the system is conserved. In its initial horizontal position, the system has gravitational potential energy but no kinetic energy. As the rod swings down, this potential energy is converted into rotational kinetic energy. By equating the initial potential energy to the final rotational kinetic energy, we can solve for the final angular speed. To find the rod's angular speed at the bottom, we will apply the principle of conservation of mechanical energy. This approach allows us to relate the initial and final states of the system without needing to calculate the changing torques during the swings. First, we set our reference point for gravitational potential energy. We will define it to be zero when the rod is hanging in its final, vertical positions. In the initial state, the rod is horizontal and held at rest, so its initial kinetic energy is zero. The rod's center of mass is at a height of L/2 above the final position. This gives it an initial potential energy of m times g times the quantity L over 2. In the final state, the rod is vertical. It has reached our zero height reference, so its potential energy is now zero. All the initial potential energy has been converted into rotational kinetic energy, which is 1/2 I omega squared. By setting the initial energy equal to the final energy and substituting the moment of inertia for a rod pivoted at its end, we find that the final angular speed, omega, equals the square root of the fraction 3 grams over L. Now that we have found the rod's angular speed at its lowest point, we can calculate the linear, or tangential, speed of any point along its length. The key relationship is that tangential speed, v, equals the distance from the pivot, r, multiplied by the angular speed, omega. For the center of mass, the distance r is L over 2. Substituting this into the equation gives a tangential speed of 1/2 times the square root of the quantity 3 times g times L. For the lowest point at the very end of the rod, the distance r is the full length, L. Since this point is twice as far from the pivot as the center of mass, its tangential speed is also twice as large, which is simply the square root of 3 grams L. This energy-based method is particularly useful here because it allows us to find the speed at a specific final position, a task that would be very difficult using kinematics, since the angular acceleration is not constant as the rod swings. In this example, we will analyze the Atwood machine, but with a crucial addition: a massive pulley. This problem is a great application of energy conservation because it connects the translational motion of the blocks to the rotational motion of the pulley. Our goal is to find the speed of the blocks after the heavier one has descended a certain distance. Our approach will be to treat the two blocks, the pulley and the earth, as a single isolated system where mechanical energy is conserved. As the heavier block falls, the system's gravitational potential energy decreases. This lost potential energy is converted into kinetic energy. Crucially, there are 3 forms of kinetic energy to account for: the translational kinetic energy of the first block, the translational kinetic energy of the second block, and the rotational kinetic energy of the spinning pulley. By setting the initial total energy of the system equal to the final total energy, we can develop an equation to solve for the final speed. We will solve this problem by applying the principle of conservation of energy, which states that the change in kinetic energy plus the change in potential energy must equal 0 for an isolated system. First, let us analyze the initial state of the system. Because everything starts from rest, the initial kinetic energy is 0. We can also conveniently define the initial gravitational potential energy to be 0 at this starting configuration. Next, we look at the final state, after block 2 has descended a distance, h. The final kinetic energy is the sum of 3 parts: the translational kinetic energy for block 1, the translational kinetic energy for block 2, and the rotational kinetic energy of the massive pulley. For the potential energy, block 1 has risen by h, increasing its energy, while block 2 has fallen by h, decreasing its energy. The net final potential energy is therefore m1gh minus m2gh. Finally, we use the no-slip condition, which relates the pulley's final angular speed, omega final, to the block's final translational speed, v final. Substituting all of these terms into the conservation of energy equation gives us a single expression that we can solve for the final speed. We can now algebraically solve our conservation of energy equation to find the final speed of the blocks. The first equation on the slide shows the result of grouping all the kinetic energy terms on the left and the potential energy terms on the right. The term in the parentheses, m1 plus m2 plus the quantity I over r squared, acts as the effective total inertia of the system. To isolate the final translational speed, Vf, We multiply both sides by 2 and then divide by this effective inertia term. Taking the square root gives us our final expression for the speed of the blocks after mass. M2 has fallen a distance. Notice that if the pulleys were massless, its moment of inertia I would be 0, and this equation would simplify to the one for a simple Atwood machine. Finally, to get the pulley's angular speed, we use the no-slip condition. Since the string's speed, Vf, is related to the pulley's angular speed, omega underscore, f by Vf equals r times omega underscore f, we simply divide our result for Vf by the radius ARE. Let us summarize the essential energy principles for analyzing rotational motion. These concepts provide a powerful alternative to using forces and torques directly, especially in situations where those quantities might not be constant. First, we defined the work done by a torque. For a very small angular displacement, d theta, the incremental work done, dw, is equal to the torque, tau, multiplied by d theta. Second, we found the expression for power. The power, P, delivered to a rotating object is the product of the applied torque, tau, and the angular velocity, omega. This is the direct rotational analog of power being force times velocity. Finally, we established the work kinetic energy theorem for rotation. This theorem states that the net work done on an object equals the change in its rotational kinetic energy. This change is calculated as 1/2 times the moment of inertia, I, times the final angular velocity squared, minus 1/2 I times the initial angular velocity squared. These principles show that energy conservation is a fundamental concept that applies equally to both rotational and translational motion. Let us wrap up by applying our energy conservation principles to 2 review questions based on the examples we just saw. For the first question about the rotating rod, the key is to correctly identify the initial potential energy. Remember that potential energy depends on the vertical height of the center of mass. If the rod starts at 60 degrees above the horizontal, you will need to use trigonometry to find this new initial height relative to the lowest point. Once you have that initial potential energy, the rest of the energy conservation setup proceeds exactly as it did in the original example. For the second question about the Atwood machine, think about how the energy is distributed. The initial potential energy is converted into the translational kinetic energy of the blocks and the rotational kinetic energy of the pulley. The moment of inertia, I, measures the pulley's resistance to rotation. If you increase I, it requires more energy to get the pulley spinning. Because the total energy is conserved, more energy going to the pulley means less energy is available for the blocks, motions. Therefore, increasing the pulley's moment of inertia will result in a lower final speed for the blocks.